Okay, guys, just open your notebook, Jupyter notebook, okay? And come to that part where Twoway ANOVA related codes have been mentioned. Okay, so just open that part. Okay, before giving explanation of that snippet of codes, I just want to give an overview of what Twoway ANOVA and different types of ANOVA are doing. Okay, in practice. Okay, how they work in practice. Okay. Look at this part. Is it visible to everyone? I think it is visible to everyone and I am audible now. So just go through what is two-way ANOVA. Look, a two-way ANOVA is an extension of the one-way ANOVA. With a one-way ANOVA, you have one independent variable, okay, affecting a dependent variable, okay. And with a two-way ANOVA, there are two independent, okay. That is two independence means two independent variable. Using a two-way ANOVA when you have use a two-way ANOVA when you have one measurement variable, that is quantitative variable, and two nominal variable, that is two categorical variable. In other words, if your experiment has a quantitative outcome and you have two categorical explanatory variables, a two-way ANOVA is appropriate. Okay, for example, you might want to find out if there is an interaction between income and gender for anxiety level at job interviews. Okay, the anxiety level is the outcome or the variable that can be measured. Okay, gender and income are the two categorical variables. Now you can say income, how? Because I make certain range of values and as impose one particular group name, that is as just I categorize the different range of income into certain groups. Okay, that's how income variable becomes a categorical variable. Okay, so your anxiety level is the dependent variable, or the outcome variable is the quantitative variable. Okay, which is continuous variable. Okay, and there are two categorical variables. One is gender, another is in your income level. Okay, these categorical variables are also the independent variables which are called factors in a two-way ANOVA. Okay, the factors can be split into levels. Okay, gender may be split into two levels, male and female. Okay, in the above example, income level could be split into three levels: low, middle, and high income. Okay, gender also could be split into three levels: male, female, and transgender. Okay, you can also include transgender. Now, treatment groups of and all possible combinations of the factors. Okay, so in this example, there would be 3 cross 3, the Cartesian product. Okay, that is equal to 9 treatment groups. Okay, like male high level, male low level. Okay, low, that is male is your gender and income level is your low. So male will be concatenated, or male will be make a combination with each level of the income group. Okay. So this is how we have found out 9 treatment groups. Okay, male low, male middle, male high. Okay, in this way. Then female low, female high. Okay, that is the way you have to form these groups. Okay, now what is main effect and interaction effect? That is very much important in case of this two-way ANOVA. So what is n-way ANOVA? N-way ANOVA, in that case, more than 2 categorical variables are present. But here, only 2 categorical independent variables are present. So it is called to be as two-way ANOVA. Okay, when more than that, then it will be called n-way. Okay, now look at the main effect and interaction effect part. The results from a two-way ANOVA will calculate a main effect and an interaction effect. Okay. The main effect is similar to a one-way ANOVA. Each factor's effect considered separately. Okay, each factor's effect is considered separately. With the interaction effect, all factors are considered at the same time. Okay, effects between the interaction between factors are easier to test if whether there is more than one observation in each cell. Okay. For the given example, multiple stress scores, that is multiple anxiety scores, could be entered into cells. Okay, if you do enter multiple observations into cell, the number each cell must be equal. Okay, so and now look at this. Two null hypotheses are tested if we're placing one observation in each cell. For example, those hypotheses would be like, for null, it will be all the income group groups have equal mean stress. Okay, and all the gender groups have equal mean stress. So this is the null hypothesis. Okay, because you are dealing with two categorical variables, and for multiple observations, when you are placing one observation in cell, and for multiple observations in cell, you would also be testing a third hypothesis. That is, the factors are independent or the interaction effect does not exist. Okay, the factors are independent. Okay, that is the gender and income level. Two factors are independent or the interaction effect does not exist. That there will be no such interaction which can affect the F statistic value. Okay, and F statistic is computed for each hypothesis we are testing. Okay. So what are the assumptions for two-way ANOVA? The populations must be close to a normal distribution. Samples must be independent. Population variances must be equal. Groups must have equal sample size. In Kruskal-Wallis test, we test the median of all groups, and in that case, we can take unequal sample size. But here, we have to take equal sample size. Okay. So samples must be independent and random, obviously, that the samples you are taking, the elements will not influence each other. Okay. So, and the population variance must be equal, that is homogeneity will be, homogeneity must be present in the elements, in the values of the data present in the population. Okay. So look, what is the statistical part of two-way ANOVA? The two-way analysis of variance is an extension to the one-way analysis of variance. Okay, there are two independent variables. Here the name two-way. So the populations from which the samples were obtained must be normally or approximately normally distributed. The samples must be independent. Okay, the variances of the population must be equal. The groups must have the same sample size. Okay, then come to the hypothesis part. There are three sets of hypotheses with the two-way ANOVA. The null hypothesis for each of the sets are given below. The population means of the first factor are equal. This is like the one-way ANOVA of the row factor. The population means of the second factor are equal. This is like the one-way ANOVA of the column factor. Okay. There is no interaction between the two factors. This is similar to performing a test for independence with contingency tables. Okay, it is expected frequency is measured through contingency table. Okay, what we have, what we covered in chi-square test. Okay, now look at these factors. The two independent variables in a two-way ANOVA are called factors. The idea is that there are two variables, factors, okay, which affect the dependent variable. Okay, each factor will have two or more levels within it. Okay, and the degrees of freedom of each factor is one less than the number of levels. That is r minus 1 if your gender has R labels, so R minus 1 be the degree of freedom for that factor, and if C is the level of the factor income level, then C minus 1 is the degree of freedom for the second factor income level. Okay, so what is the total number of degree of freedom? That is R minus 1 into C minus 1. Okay, so treatment groups are formed by making all possible combinations of the two factors. Okay, for example, if the first factor has 3 labels, second factor has 2 labels, then there will be 3 into 2 equal to 6 different treatment groups. Okay, as an example, let's assume we are planting corn. Okay, the type of seed and type of fertilizer are two factors. Okay, we're considering in this example. This example has 15 treatment groups. There are 3 minus 1 go to 2 degrees of freedom for the type of seed, and 5 minus 1 4 degrees of freedom for the type of fertilizer. Then there are 2 into 4 equal to 8 degrees of freedom for the interaction between the type of seed and type of fertilizer. Okay, so look at this. The data that actually appears in the table are samples. In this case, 2 samples from each treatment group were taken. Look, multiple observations have been taken into a cell. Okay, that is more than one observation. That is the first the value of the first sample for fertilizer 1 and seed A type, and this is the value 110 for the second sample. Okay, so this is how we fill up. Now look at this main effect. The main effect involves the independent variables one at a time. Okay, just wait. Okay, look, the interaction is ignored for this part. Okay, just the rows or just the columns are used, not mixed, not a mix of both. Okay, this is the part which is similar to the one-way analysis of variance. Each of the variance calculated to analyze the main effects are like the between variances. Okay, now look at this interaction effect. The interaction effect is the effect that one factor has on the other factor. Okay, the degrees of freedom here is the product of the 2 degrees of freedom for each factor. Okay, product of 2 degrees of freedom of each factor, that is R minus 1 into C minus 1. If your first factor has R label, so R minus 1 be the degrees of freedom of first factor, and if the second factor has C level, so C minus 1 is the degrees of freedom of second factor. So the product of these 2 degrees of freedom, that is R minus 1 into C minus 1, okay, is the degrees of freedom of this interaction effect. Okay, so within variation, what is the within variation, what is the between variation? Come to that part. So the within variation is the sum of squares within each treatment group. Okay, you have one less than the sample size. Okay, remember all treatment groups have the same sample size for a two-way ANOVA. for each treatment group. Okay, the total number of treatment group is the product of the number of labels for each factor. Okay. That is, if you have 3 labels for the first factor and 3 labels for the second factor, then 3 into 3 equal to 9 is the total number of treatment groups. Okay, understood. The within variance is the within variance divided by its degree of freedom. Okay, this within group is called, or the within group variation is called the error. Okay, now look at the F tests. There is an F test for each of the hypotheses, and the F test is the mean square of each main effect and the interaction effect divided by the within variance. The numerator degrees of freedom comes from each effect. Okay. And the denominator degrees of freedom is the degrees of freedom for the within variance in each case. So two-way ANOVA table. This is the two-way ANOVA table. Look at this. It is assumed that main effect A has A labels. Okay. So A has A minus 1 degree of freedom, main effect B has B labels. So B factor has B minus 1 degree of freedom. N is the sample size of each treatment, and the N, this N equal to AB. Okay. That is the treatment group. N is the total sample size. Okay. And so you can say, notice here this N is this total sample size. Okay, this. So N is the total sample size. Notice that the overall degrees of freedom is once again 1 less than the total sample size. Okay. This lowercase n is the sample size of each treatment. Okay. And n equal to AB. Okay. Where n is the total sample size. Okay. So the overall degrees of freedom is once again 1 less than the total sample size. Okay. Look at these parts. Main effect for A, main effect for B. Okay. This is your sum of square association for the labels of factor A divided by within error variance. Okay. This is for the between variance for different levels for the factor B by error within variance. Okay. And for the interaction effect, sum of squares for A into B. Okay. And divided by the within variance for the interaction effect. Okay. Okay. And now this is within. What is the within? N minus N is the total, and minus AB. Okay. And AB into N minus 1. Okay. So sum of squares by this degree of freedom. Okay. Look, this is sum of others. Okay. N minus 1. Okay. It is your degree of freedom. Okay. Because N equal to AB into N, na? N is the sample size of each treatment. So when you replace N with this, so N becomes this. Okay. look. So look, this is n, okay, and this n is the total sample size, okay. The following results, look at the summary part. The following results are calculated using the Quattro spreadsheets. Okay, this is one kind of spreadsheet which we use. Okay, if you search on Google, you can get these things. Okay. It provides the p-value for and the critical value and for alpha 0.05. Okay, so this is your sum of squares. Okay, this is degrees of freedom. Okay, and for the seed factor, for the fertilizer factor, for the interaction, that is seed into fertilizer. Okay, and this is the within variation. So this is the total. Okay. From the above results, we can see that the main effects are both significant, but the interaction between them is not. Look, the interaction between them is what? That is 1.973, which is less than the F critical value 2.641. Okay, F statistic is less than the critical value 2.641. And look at the p-value 0.122, which is greater than 0.05. So the interaction does not have any significant impact. Okay, but the seed and fertilizer value, look, for the for F statistic on the seed factor, you can see that 28.283 is greater than 3.682 and 12.393 is greater than 3.056. Okay, so look at this. This F statistic is greater than the F critical value. Okay, and this F statistic for the fertilizer factor is also greater than the corresponding F critical value. And look at the p value. 0.0008 is too small than the given alpha 0.05, and also the 0.000119 is also too small than the given alpha 0.05. So here we can say that the main effects are both significant, but the interaction between them is not. That is, the types of seed are not all equal, and the types of fertilizers, that is the different levels of fertilizer used here, are not equal. Okay, in terms of mean, but the type of seed does not interact with the type of fertilizer, because the third hypothesis is used in case of Twoway ANOVA to prove that whether there is interaction lying between the two factors. So in the when we have to prove the third hypothesis, we have found out that no, the type of seed does not interact with the type of fertilizer. That means the interaction between them is not significant. Okay, now look at this. Just wait. Look at this, sum of squares in ANOVA and regression. When you conduct a regression, then you will have to learn in detail about this sum of squares in ANOVA. But look at that, actually the output what you are getting there is also the same as you have observed right now in ANOVA table. Okay, so look at this. As you can probably guess, the things get a little more complicated when you are calculating sum of squares in regression analysis or hypothesis testing. It is rarely calculated by hand instead of software like Excel or SPSS usually used to calculate the result for you. For reference, sum of squares in regression uses this equation. Okay, y minus y bar whole square, that is actually ordinary least square method. Okay, we will learn in detail in linear regression part. So y is your value. Okay, every data point, and y bar is the grand mean, you can say. Okay, so y minus y bar. Okay, so it is the mean and mean of the samples, and this is the summation of y hat is your predicted value. Okay, that is expected value, the expected value minus mean plus your observed value minus expected value. So this is something your this part, the right hand part, y minus y hat is your within error, you can say. Okay, within error part, and this is your this y predicted minus y bar is something which is your between group error. Okay, between factor variations, whatever you want to say. So ultimately the summation of these two will give you the total variation, that is the main mean of the values is deviated from the actual of the actual data points. By what extent, that is what we need to compute. Okay, so and in ANOVA it is calculated with the total sum of squares equal to treatment sum of squares. Okay, you can say that not this, it will be your SSA. Okay, so this is something plus SS of the residual error, that is you can say. Okay, or you can write here SST, but actually I want to change this T to A to, so that you cannot misread it as total sum of square. Actually this T stands for treatment. Okay, actually we are going to use SSA or something SSB like that. Okay, when we want to define the B2 group, when we want to define between group variation as SSA or SSB. Okay, rather than SST, but here T does not mean total. Okay, this is the total sum of squares that can be written as SST, but here this T appears because treatment word is used here. Treatment sum of squares is used here. So to indicate this treatment part, it is mentioned within the parenthesis as SST. Okay, and look at this. This is your residual error, that is standard sum of squares for errors. This part. Okay, so. So look at this part, the y minus y bar. Okay, this is your observed value and this is your predicted value, and the whole square part is your sum of squares for error. Okay, so look at this y ANOVA. You can better say y hat is your mean for the each factor, not the grand mean. Okay, you have learned about the grand mean, group mean, so and the individual data value. So this is the same case. When you do regression part, you can get an output of ANOVA table, and you have to interpret on the basis of regression. Okay, so that's a different thing, but this is how this ANOVA the formula of ANOVA works in regression or hypothesis testing. Okay, so why ANOVA is called analysis of variance? So I have already told you. I have already told you. So just go through. you have understood the just remember the ratio MSA by MSE, so you can understood. I have already explained that part. So here we just compute the mean square of association and mean square of error and take a ratio of both to compute F statistic, and then we can decide whether the population means across the groups are equal or not, and we reject null or fail to reject null based on the critical value of based on the value computed, that is the F statistic computed, and compare it to the F critical value, or you can use another approach, that is the p value approach. So based on that we decide. So here the variance is used to compute that mean square of association or between group variation and the within error variation. So within group variation, okay, that is the error part. So that is why an analysis ANOVA is called analysis of variance. We covered this part. So now look at this. What exactly is required by the homogeneity of variance assumption? Okay, I told you now the population variance must be the. Look at this assumption part. The variances of populations must be equal. Okay. So what is that? Look at this part. Look at this part. This means that as the value of your independent variable changes, the amount of variability in your dependent variable remains approximately the same. Okay. That is the variance of variance across the groups. Okay, of the corresponding population are equal. Okay. The amount of variability in your dependent variable remains approximately the same. Okay. Suppose first your independent level gender has male female. So if male and your income level is low, middle, high. Okay, so if it gets changed from low to middle and male to female, okay, so female and middle will be the new group, but for the male and low and for the female middle group, the change may happen, but the amount of variability in your dependent variable, okay, that is your the score of anxiety level, okay, which is a quantitative variable or continuous variable, that the variability among that among the different data elements present in the output variable, which is a quantitative one, or here it is your anxiety score, is executing equal variance. Okay, is that is not executing, that is it is having equal variance. Okay, that so the variable of the that is the dependent variable will remain approximately the same in terms of variance. Okay, the amount of variation will not get changed if the value of your independent variable, that is the level of your independent variable, gets changed from one value to another. Okay, that is if your the level of one independent variable gets changed from one particular value to another, okay, that is the level gets changed from low male, low income group, and gender for gender male to female gender and middle income level group, then the variability of the dependent variable, that is anxiety score here, remains approximately the same. Okay, that is your homogeneity of variance. Okay, and so let's say your independent variable is the amount of fertilizer you are adding to a plot. Okay, the dependent variable is the growth rate of the plants in your plot, and you have 3 replicate plots per treatment. Okay, so then let's say what you found, that adding the low level treatment amount of fertilizer resulted in growth rates of 3, 4, and 5 centimeter per week. The mid level treatment resulted in 5, 6, 7 centimeter per week, and the high level treatment resulted in 8, 9, and 10 centimeter per week. Okay, each of the treatments, even though they have different means, all have same variance. Okay, look at the variance part. Okay, if you look at the variance part for 3, 4, 5, and 5, 6, 7, and 8, 9, 10, then the variance is same. Okay, therefore they meet the assumptions of homogeneous variance or homogeneity of variance. Okay, so in statistics, ANOVA or analysis of variance is a test used to analyze if there is a significant difference between different groups. Okay, that is different groups means different groups of the categorical variable with respect to a specific metric, that is the output variable or quantitative variable. Okay, it relies on building a linear model where the categorical variable is the explanatory variable, because it explains that by how much the quantitative variable has by how it can make a significant difference on the quantitative variable. Okay, that's why this categorical variable is called the explanatory variable. Okay, okay, and the quantitative is the response variable. Okay, ANOVA, so just keep this in your mind when you do regression part. This categorical variable is your explanatory variable, and the because it measures or explains that how much difference it can create to the quantitative or response variable on the response variable, and the output, which is a quantitative variable, is called the response variable. Okay, ANOVA compares means of different groups and check whether the differences are statistically significant or not. Okay, so the different types of sum of squares then arise depending on the stage of model reduction. Okay, that different types of sum of squares then arise depending on the stage of model reduction at which they are carried out. Okay, so look at this. Just remember there was a type equal to 1, 2. When you call the ANOVA underscore LM, LM stands for linear model, and pass the results. Okay, that is that you have obtained after the fitting the model dot fit. Okay, so you have mentioned also the you have to pass a certain value to the parameter type. I have told you type maybe 1, 2, 3. Okay, when I just show you the notebook, then you can remember that part. Okay, I am showing you first. Okay, this is for the two-way ANOVA, but in one-way ANOVA we have found, look, this type equal to 1. So what is that? We have to learn these things first. Okay. Okay, the different types of sum of squares, okay, that arise depending on the stage of model reduction at which they are carried out. What are those? Type 1, also called sequential sum of squares. So SS of A for factor A, SS of B provided or the SS of A has already done. Okay, for factor B, SS of interaction of AB provided that the sum of squares for factor A and sum of squares of factor B are already done. The pipeline just tells you that which factors need to be done before. Okay, so this is the case. This is the sequential order of sum of squares. That is, this tells the main effect of factor A followed by the main effect of factor B, and the main effect of A followed by the that is the main look followed by the main effect of factor B after the main effect of A. That is, first you have to compute the main effect of factor A, then after computing main effect of A, you have to compute main effect of factor B, and then followed by the interaction, and then it is followed by the interaction effect AB. That is after the main effects. After the main effects, you have to compute the interaction effect of AB. Okay, because this sequential nature and the fact that the two main factors are tested in a particular order, this type of sum of squares will give different results for unbalanced data. That is where the sample size is not equal. Okay, so for unbalanced will give different results for unbalanced data depending on which main effect is considered first. Okay, for unbalanced data, this approach tests for a difference in the weighted marginal means. In practical terms, this means that the results are dependent on the realized sample size. Okay, namely the proportions in the particular data set. Okay, in other words, it is testing the first factor without controlling for the other factor. Okay, we don't need to do we don't need to go in detail, because just look in this part. This means that the results are dependent on the realized sample size. Okay, because the sizes are unequal, and namely the proportions in the particular data set. Okay, and in other words, it is testing the first factor without controlling for the other factor. Okay. Okay, now look, note that this is often not the hypothesis that is of interest when dealing with unbalanced data. Okay. Now, what is type 2? For factor A, factor B, this type of test for each main effect after the other main effect. Look, that is that is first we compute the main effect for factor A, provided that already you have computed the main effect on B, and SSB of A, that is, each computes the main effect of for factor B, provided you have already computed the main effect of A factor. Okay. Okay, Shima, what happened? Shima, you
No,
just
ma'am, nothing.
Rudramuni. Oh, Rudramuni, just mute your video. Just stop your video. Rudra, just stop video. Rudra, what are you doing? Rudra. Rudramuni. Yes. Look. Look. So this type of test for each main effect after the other main effect. So this type tests for each main effect after the other main effect. Okay. Note that no significant interaction is assumed. Okay. In other words, you should test for the interaction first. Okay, this is SS of AB, provided A and B. The main effect for the factor A and B has already done, and only if AB is not significant, continue with the analysis of main effects. Okay, if there is indeed no interaction, then type 2 is statistically more powerful than type 3. Okay, this is the case. Computationally, this is equivalent to running a type 1 analysis with different orders of the factors, okay, and taking the appropriate output. Okay, the second, where one effect is run after the other. Okay, so this is the case for type 2 error. Sorry, for type 2 sum of squares computation. Okay, and now look at the part. Type 3. This is a type of look. SSA provided main effect of B and interaction effect for the AB will be done. Then the main the main effect of factor A is computed. Then main effect of factor B is computed, provided main effect for the factor A and interaction effect for the interacting group AB has already been done. Okay, so this type of tests for the presence of the main effect after the other main effect and interaction. This approach is therefore valid in the presence of significant interaction. Okay, however, it is often not interesting to interpret a main effect if interactions are present. Okay. Generally speaking, if a significant interaction is present, the main effect should not be further analyzed. Okay. If the interactions are not significant, then type 2 gives a more powerful test. Understood why this type 2 gives a more powerful test? Because when the interactions are not significant, then obviously the main factors need to be checked. That is, the main effect of the factors need to be checked whether they have significant impact on the response variable or not. So that's why they will give more powerful test. Okay, they will give more statistical power. That's why they are this type 2 gives a more powerful test. Okay, when data is balanced, the factors are orthogonal. Okay, that is, variance becomes statistically independent. Okay, data is balanced means sample sizes are equal. Okay, then type 1, type 2 and type 3 give the same results. Okay, so it will not give any different results if you know the sample size is equal. Okay. Now tuck is HSD post HOC comparison. In Kruskal-Wallis test, I told you that we don't know which groups are different. We know there is a significant difference between the two groups. At least between the one groups. If there are more than two groups, then you can say at least one group is significantly different. Okay, that's why the population medians are not equal. When we did the Kruskal-Wallis test, which is a non-parametric test where we need to check the population medians across all the groups are equal or not. So, but we cannot learn which groups are different. Okay, and in the case of ANOVA, we cannot learn which groups are different. Okay, we have to conduct independent 2T test or sample 2T test. Okay, just remember that part. I am showing you. Look at this part. This part checks each group whether they are which group is significantly different, and we have found out this center C has made this significant difference. So similarly, in case of Twoway ANOVA, we have to do this test, but here we use not 2T test because there are two categorical variables are used. So we do this Turkey's HSD post HOC comparison. You can conduct this for Kruskal Valley's test also if you want to learn which groups are different. Then you can use this. Okay, so this is the way. Okay, so this is suppose this is some kind of drug and this is the dose. Okay, and you need to know the results. Look, high, low, high, placebo, low, placebo. Okay, so this is group one, group two, lower boundary, upper boundary, and do you have to reject or not? Look, so each factor has an independent significant effect on the mean crop yield. Okay, while it is good to know if there is a statistical significant effect on some intervention on the outcome. Okay, it is as important to know the size of the effect the intervention has on the outcome. Statistical significance does not always translate into a large effect in the world. Okay, this is important to consider because everything costs money and money and time. So to see this, we can calculate the effect size. Okay, the following code uses the ANOVA table produced by stats model and appends the effect size measures. Okay, theta squared and omega squared. We will learn that part in linear regressions mainly. Look, group one, group two, mean difference this lower upper. Okay, so there is statistically significant difference between the mean crop yield between fertilizer A and B. Fertilizer A yields significantly A yields a significantly higher crop yield than fertilizer B. Okay, Just wait. I'm trying to connect. I'm trying to share my screen. Guys, there will be some internet, there is some internet issues, and you all will have to wait for 10 minutes. Okay. 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 So the logic that I'm about to explain can be used to expand from a two-way ANOVA to an n-way ANOVA, where n is n is any number of factors. Okay. So to talk with these, to talk through these, imagine okay, we have independent variable a with two labels a1 and n2, and independent variable b with two labels b1 and b2, with our dependent variables which is most commonly annotated as okay, which is most commonly annotated as y. Okay, we want to see the effects of a on y, b on y. Okay, and to test if there is an interaction effect of a and b on y. Okay, with this design, the following hypotheses are being tested. Okay, for the first hypothesis, there is not interaction. In alternative, there is an interaction. Main effect of factor A. Okay, that is the population mean for group A, and for the different for the factor of or for the label of factor A and for the label 2 of factor A is equal. Not all the means are equal. Main effect of factor B, that is the factor 1, that is the label 1 of factor B, and level 2 of factor B are equal in terms of mean or not equal. Okay, these are the three set of hypotheses need to be checked. Okay, so the assumptions of homogeneity of variance, that is what we have covered this, but here you have to learn the about the sample size. Look, the assumption of homogeneity of variance is an assumption of the independent sample t-test and ANOVA, stating that all comparison groups have the same variance. Okay, the independent sample t-test and ANOVA utilize the T and F statistic respectively, which are generally robust to violations of the assumptions as long as group size are equal. Okay, equal group size may be defined by the ratio of the largest to smallest group being less than 1.5. Okay, if group size are vastly unequal and homogeneity of variance is violated, then the F statistic will be biased when large sample variances are associated with small group size. Okay. When this occurs, the significance level will be underestimated. Okay, which can cause the null hypothesis to be falsely rejected. Understood? On the other hand, F statistics will be biased in the opposite direction. If the large variances are associated with large group size, this would mean that the significance level will be overestimated. This does not cause the sample problems as falsely rejecting the null hypothesis. However, it can cause a decrease in the power of the test. Okay. Understood? That is what will be the result for underestimating and overestimating the F statistic. Ujjal, is it clear? The last lines. That is when your large variance is associated with small group size, the significance level will be underestimated. Okay, which can cause the null hypothesis to be falsely rejected. Okay, and on the other hand, the F statistic will be biased in the opposite direction if large variants are associated with large group size. This would mean that the significance level will be overestimated. This does not cause the sample problems as falsely rejecting the null hypothesis. However, it can cause a decrease in the power of the test. Have you understood these lines? Ujjal, have you understood these lines?
Ma'am, understanding, but facing some difficulty in understanding this last line, ma'am.
Try. Explain me. I'm giving you 2 minutes. Okay, 3 minutes. Shima also try. Ujjal, I want answer from you. Okay, Ujjal, tell me.
Ma'am, actually, if there is a problem of unequal or homogeneity of variance like heteroscedasticity, then F statistic will be overestimated. Sorry, underestimated. Like we underestimate our confidence interval level, and
Okay.
that
Okay,
that
okay, okay. I'm giving you one note explanation on notepad. Okay, just wait. Look at this. Okay. Suppose first sample. Okay. First sample or first group, whatever you can say. Okay. Now second sample. Okay. So and third. Okay. Okay. So look, the variance here. Just I do one thing. Mm, better I take another one. Okay. Okay. So look, fourth sample is having higher variance. So large variance is observed with small sample size. Ujjal, can we say that large
yes,
variance
ma'am.
is observed with this may happen. This is your first case, okay,
Yes,
where
ma'am.
underestimation takes place. So when large variance is observed with small sample size, so in that case, it will just make the group variance. It will just create group variance higher compared to the within variance while computing F statistic. So if the upward part, the numerator becomes larger than the denominator, resulting in higher F statistic value. Am I right?
Yes, ma'am.
Because your numerator is mean square of association, that is between group variation, that becomes larger because here this large variance is associated with small sample size. Okay, so if this size happens, so within group variation is smaller compared to that between group variation. So so we can say also in a reverse manner that the mean square of association of between group variance becomes larger compared to the within group variation, that is the error term. So that happens due to these large variance effects which is associated with the small sample size. So that is the reason for this unbalanced data to make the model unbalanced. That is the F statistic which we have computed here is underestimated. Okay, understood.
Yes, ma'am.
And now if in the because in that case what happened, you whatever p value you are getting in this case, okay, I will do this thing later. First understood this one. When you compute this, okay, a statistics and the corresponding, so your if statistic becomes greater than the if critical value, okay. Whatever if statistic you have computed here, that is greater than your f critical value, and if you look at the p value, that is too small compared to the alpha 0.05, say you can take 0.01, whatever I have taken here alpha 0.05. So if you go if you conduct this test, if you find out such results where p value is less compared to this, so you just tell the yes, I want to reject the null. So that is something your underestimation, okay. That happens due to underestimating the if statistic value, okay. So now what is overestimation? When suppose some sample that is large variance associated with, this is the case, associated with small sample size, okay. Now if my second case is with large sample size, okay. So when this happens, so look, I will just change something. Look, that will be my values, okay. And look here, we will do one thing. So look, large variance is observed with large sample size. So what happens? Obviously, when you compute your F statistic, okay, that the F statistic, the value of F statistic, is less than F critical. Okay, so you can retain with the null. Understood? If it is less than the F critical value, then you can retain the null hypothesis. So when you can retain the null hypothesis, that means your power gets decreased. Your power of the hypothesis gets decreased. Understood? Power means what? When you can choose the alternative hypothesis when you fail to reject when you can reject the null. But when you fail to reject the null, then obviously you can retain the null, but that ultimately results in decreased power of the test. So that is your overestimation of F statistic value. Understood?
Yes, ma'am.
Because this large variance associated with the large sample size creates impact on the F statistic, okay. That is the mean square variance, okay. So when so your within error variance becomes larger, and the numerator part between group variance becomes smaller, okay. So it will ultimately in what? That is lower value of F statistic. So when you compare the value F statistic and F critical, then you have find out then you have to find out the one thing, that whether F statistic is less or greater. So F you have found out here that F statistic is lower compared to F critical value. So you can retain the null. So it obviously also suggests that there is a decrease in power of the test. Have you understood?
Yes, ma'am.
Okay. So this is that's it for this Twoway ANOVA. Okay, I have okay. Tell me this part. I have covered this part to reject, and why do we not reject here? Look here, rejection is true. Okay, and this is false. Look, I have told you now. The post HOC comparison part, we it is tested to this test is conducted to determine whether which two groups are different and which two groups are significantly different, and then we can decide the null hypothesis. That is we have to decide whether the null hypothesis is true or not. So that is whether we retain the null hypothesis or we reject the null hypothesis at a given alpha level. So how can you check this? Tell me. Look at this. There is a statistically significant difference between there is a statistical significant difference between the mean crop yield between fertilizer A and fertilizer B. What is the mean difference? Minus 3.72. Okay. So fertilizer A yields a significantly higher crop yield than fertilizer B. Okay. How can you say that? Tell me. Here nothing is mentioned like critical value, no p value. Then how can you determine that is fertilizer A yields significantly higher crop yield than fertilizer B? Tell me, tell me. Ujjal, Shima, tell me. Are you there, Shima?
Yes,
Shima,
ma'am. Yes.
tell me, how can you understand? That is the fertilizer A yields significantly higher crop yield than fertilizer B. And in the second part, it is mentioned there is not a statistically significant difference in the mean crop yield between the amount of water used, high and low, high amount of water, low amount of water. That is not significant. So we reject. Okay, so it becomes false. Rejection is true, that is we have to reject the null, and here rejection is false, that is we fail to reject the null. Understood? Here rejection true means what? That is yes, we reject the null hypothesis because there is a statistically significant difference and exists between the group A and group B, and here rejection is false means we fail to reject null. Okay, that is there is not statistical significant difference in the mean crop yield between the amount of water used. So how can you learn, how can you understand from the given data? Tell me. Ujjal, you can try. You all have to be very clear in explaining these parts. Tell me.
Ma'am, here in upper, lower is minus 7.36 and upper value is minus 0.07, which is greater than lower. Then ma'am, and ma'am, in lower, here lower value is minus
What
7.
is your telling? Upper is greater than lower, we know. In both the cases, upper is greater than lower.
Yes, ma'am.
So that is not the reason. Ujjal, try. You have not gone through. I have understood. Ujjal,
Yes.
have you had any idea on that?
No, ma'am.
No. So, do you find any relation between lower and upper? How can we interpret this population means equal? Look, either I have in the beginning of ANOVA session, I have told you there are two ways. Okay, just wait. One way ANOVA na. Straight. I have these things. This. Just. Look, if mu1 is mu1 the population mean, okay, mu1 equal to mu2 population mean of level 1, okay, for the group of or for group A or whatever. So I am considering my first factor A, and it has two levels. So I have to check whether the population means are equal or not. This is my null. Okay. Okay. So how can I, and in the alternative, we can write this. Not equal to, okay, mu2. So this is the general, this is the general form, okay. You can write in this way also for different groups, mu1 equal to mu2 equal to mu3 equal to ... okay, mu k, okay. That is what you can write in your null. That is mu I equal to mu j. Okay. But in alternative, at least one of the means is not equal. Okay. So this is your null, and you can write in alternative mu I not equal to mu j for at least one j. Okay. Like in this way. Or you can write in this way, summation of I'm just showing you that part, then you can understand. Just remember the null hypothesis. Okay. In the alternative hypothesis, alpha j is not equal to 0 for at least one j. Okay. Now, just remember the two population means are equal, mu1 equal to mu2, not equal, mu1 is not equal to mu2, which we have done in 2T test. Okay. So, and mu1 minus, so you can rewrite this null and alternative hypothesis in the following way also. Mu1 minus mu2 equal to 0. That is the difference between two population means is equal to 0. Okay. And mu1 minus mu2 is not equal to 0. That is the difference between the two population means is not 0. Okay, in the alternative, mu1 minus mu2 is not equal to 0. And in the null hypothesis, mu1 minus mu2 equal to 0. Understood? From that, you can use these things to try to understand why we have to write in the rejection column true and false in the given example. Okay. I'm sharing my screen. Now tell me, Ujjal. So mu1 minus mu2 equal to 0 is your null, and mu1 minus mu2 is not equal to 0 your alternative hypothesis. So now tell me, I have given you a hint. So now just answer to me why in this reject column it is mentioned true, and in this reject column it is mentioned false. That is, you cannot reject the null here, and in the first one you have to reject the null. Okay. So now, can you answer to me, Ujjwal? Ujjwal.
Yes, ma'am. I'm good. 2 minutes.
Hmm. Shima also try. I have told you, na, mu1 minus mu2 equal to
Yes,
0 in case of null. Because if you equate both the sides, mu1 equal to mu2, so you can also rewrite the equation in this way: mu1 minus mu2 equal to 0 in your null hypothesis, and in your alternative hypothesis mu1 minus mu2 is not equal to 0. So now tell me, look, there is a lower column, upper column. Look at the values of lower and upper column, please.
Ma'am, because they're less than 0, that's why.
Hmm? What? Tell me. Tell me, tell me. Tell me.
Ma'am, in above case, the two means are different. Two mean values are different. मतलब group A and group B mean values are different. That is why here null is true. Null
What
rejected.
is this? Two mean values are different. Two mean values may be different. How does it affect? What do you mean by confidence interval?
How confident we are about the result?
Hmm? No, that is confidence level.
Ma'am, here it is not
Talking
equal to
about
0. There.
confidence interval.
Interval between upper bound and lower bound, ma'am.
That means what? That is a range of values that is likely to contain the population parameter with a certain level of confidence, say 95%. So that means out of 100 times of your trial, you are getting 95 times the population parameter lying in your confidence interval. Okay, understood? So now tell me, Okay, tell me, Shima and Ujjal, are you there?
Yes, ma'am.
Tell me what kind of value exists between lower and upper bound? Is it the difference of mean or only mean? Tell me.
Ma'am, from mean, right?
Hmm? You have learned ANOVA, one way, two way, and now you cannot explain this little part. What does this confidence interval is going to hold? Okay. What population parameter is likely to lie within this confidence interval? What is that? That is mean or difference in mean?
Difference in mean.
Yes. Understood. It is not only mean because you have considered here group 1 and group 2. So difference in mean is likely to lie within this confidence interval. Okay. So look, there is a value 0. Okay. Understood. Which is present between this lower and upper or not? Tell me. Tell me, 0 is present between this lower and upper or not?
No,
Ujjal?
ma'am.
Hmm?
No.
Okay, so what does it mean? Mu1 minus mu2 is
Okay, is not equal to 0.
is not equal to
Sorry, yes, is not 0.
there is. Tell me, is there any value 0 present between lower and upper?
No, ma'am.
So what does it suggest? Mu1 minus mu2 not equal to 0 or mu1 minus mu2 equal to 0. Which one does it suggest? You have told us, Shima just replied, that is the mean in difference is likely to lie within this range. So if the mean in, that is the difference in mean, okay, difference in population mean is likely to lie within this confidence interval and there is no 0. So mu1 minus mu2 is not equal to 0 or mu1 minus mu2 is equal to 0. Tell me which one do you want to take? Why? Simple question. Shima, mu1 minus mu2 is not equal to 0 or mu1 minus mu2 is equal to 0. Which one is right?
Ma'am, not equal to 0.
Yes. Ujjal, have you understood?
Yes.
0 is not, 0 is not present there. So mu1 minus mu2 is not equal to 0. Understood? Because you are searching what parameter? Difference in population mean, not only any specific mean of a particular group. It is the difference in mean, which is likely to lie within this range. Okay. If mu1 minus mu2 is not equal to 0, that means your alternative hypothesis is to be accepted. That means you can reject your null. That is why in the reject column, true is mentioned. Okay. That is, you can reject your null. There, it can suggest that there is a statistical significant difference between the mean crop yield between fertilizer A and B. So 0 means what? There is at least a reasonable 0 is present, which makes the mean difference. Okay, which makes the mean difference between these groups is equal to 0, and also suggests that there is no relation between the groups. Okay, so that is the impact of these groups on the yield, on the mean crop yield is not if the 0 is present. But here in this case 0 is not present. So we can say yes, there is no as such value, that is the mu1 minus mu2 is not does not become zero for there is no such reasonable zero present within the range. So we cannot say that at any point of time there will be no there will be such situation where we can find there is and say that there are no such significant impact on the mean crop yield. So here what we have found out, the difference mu1 minus mu2 is not equal to 0. So it suggests that we can reject the null, okay, because there is a statistically significant difference, okay, because there is no mean difference becomes equal to 0. Okay, so there it also suggests there is obviously some one has better performance than the other one. So here we have find out that the fertilizer A is significantly better, higher crop yield than the fertilizer B. Okay, so if it is the case when your mu1 is greater than mu2, okay, suppose mu1 minus mu2 is not equal to 0, then you have to check whether mu1 is greater than mu2 or mu2 is greater than mu1. That is that you have to compute it by just calculating the population mean, or you can calculate sample mean and then predict the population mean also. That's a different thing. But when you see that mu1 is greater than mu2, so you have to learn the significance, okay, that is whether the impact is significant or not. So in order to test that you have to conduct this 2K HSD. Okay, so here when you find out the mu1 minus mu2 is not equal to 0, so there is no as such reasonable zero which can suggest that yes, there will be no relation. When there will be a reasonable zero, then we can say that there is no relation between the two groups. Okay, for at least there is a chance that the mean difference becomes 0 in that range. Okay, there is a chance of getting a reasonable 0 when you are conducting the test. There is a chance of getting a reasonable 0 if you find 0 in the range. So you can say that there is a chance of getting a reasonable 0 which makes the mean difference equal to 0, suggesting that there is no relation between the groups which can have significant impact on the mean crop yield. Okay, so here it is it does not contain any 0, so that means mu1 minus mu2 is not equal to 0. Then you have to compute the value of mu1 and mu2. Okay, and you can say that yes, fertilizer A yields significantly higher crop yield than fertilizer B. It may happen that mu2 is greater than mu1, then you have to tell it in a reverse way, that then you have to tell fertilizer B has a higher impact in crop yield than the fertilizer A. Understood? Now come to the second part. Here look, we in there is we have deduced we have concluded here that there is not a statistically significant difference in the mean crop yield between the amount of water used. A high amount of water and low amount of water are the two groups. Okay, look at the differences between lower and upper bound. Here 0 is included. So at one point of time when you're conducting the trials of this test, then you can get a reasonable 0 at one point of time. You can get a reasonable 0 suggesting you that suggesting you that the the mean difference for the two factors high and low, that is mu1 minus mu2, becomes 0. Okay, so obviously it tells you that there is no effect or there is no significant effect of these two groups on the mean crop yield. Okay, so we can here in the reject column we have mentioned false. That means what? That we cannot reject the null. We fail to reject the null. We have to retain the null hypothesis. So we have concluded here that there is not a statistically significant difference in the mean crop yield between the amount of water used. Understood?
Yes, ma'am.
Yes, ma'am.
Yes, you have to clear all these things, okay? Otherwise, in the regression part, in the classification part, you face a lot of problem, okay? You come across a lot of things, okay, and then you just get trapped into such a situation where you cannot understand what does this value actually mean and how to interpret, and then you cannot build your model properly, okay? No, I have to tell you one thing also. Look, just look. This is something, types of tests, okay? One way ANOVA between groups when you used when you want to test two groups to see whether there is a difference between them, and two-way ANOVA without replication and two-way ANOVA with replication, okay? So used when you have one group and you are double testing that same group, okay? You are testing one set of individuals before and after they take a medication to see whether it works or not. Two ANOVA with replication, two groups, and the members of those groups are doing more than one thing. Two groups of patients from different hospitals trying two different therapies. So here two categorical variables come into picture, but in case of with replication, but in case of without replication, you are conducting the test on the same individual or subject at different point of time, or when they have if after they are after undergoing a specific procedure, you want to test the effect of that procedure or impact of the training on these subjects or individuals take place or not. So this is the case. Okay, so I will talk about a little bit more about different types of tests. So okay, just go through this part. Okay, so you have understood now. One way ANOVA is used to test two or more groups. Okay, to see whether there is a difference between them, and two-way ANOVA without replication and two-way ANOVA with replication. So now now look at this ANCOVA. So what is this? The obvious difference between ANCOVA, ANOVA and ANCOVA is in the letter C. Okay, is the letter C, which stands for covariance. Like ANOVA, analysis of covariance as a single continuous response variable. Okay, unlike ANOVA, ANCOVA compares a response variable by both a factor and a continuous independent variable. Example, comparing test score by both level of education and the number of hours spent studying. Okay. The term of the continuous independent variable used in ANCOVA is a covariate. Okay. Understood? These are the levels of the factor. Okay. Education level, high school, college degree, graduation, okay, post-graduation, whatever you want. Okay. And covariate is your number of hours study, number of hours spent in study. Okay, so these two factors jointly make an impact on the response variable, that is test score here. Okay. Now look at this MANOVA. What is it? The obvious difference between ANOVA and a multivariate analysis of variance, that is called to be MANOVA, is the M, which stands for multivariate. In the basic terms, MANOVA is an ANOVA with two or more continuous response variable. Okay, response variable is what? Dependent variable. Okay, your Y. Okay, X is your independent variable, Y is your dependent variable. You know now Y equal to f of X. The function of Y is Y is the function of X. Okay, so Y is your continuous response variable. There the number of continuous response or dependent variable is two or more. Okay, like ANOVA, MANOVA has both a one-way flavor and a two-way flavor. Okay, the number of factor variables involved distinguish a one-way ANOVA, a one-way A MANOVA from a two-way A MANOVA. Okay. Suppose only one factor, one categorical variable is present, so it will call one-way A MANOVA. If more than one factor is involved, then it is called, if two factors are involved, then it is called two-way MANOVA. If more than two, then it is called N-way A MANOVA. Understood? So look at the example. This is your one-way ANOVA example, independent variable, dependent variable. Okay. Here, this is test score and this is annual income. If you cannot view this, I am just increasing. I increase. Just wait. Okay, I am just telling you, it is not visible to you. Okay. So look, this is your level of education, high school, college degree, okay. And these are the two wise. One is test score and this is annual income. Okay. So in one way, M ANOVA compares two or more continuous response variables. Okay. And look here, look here, test score and annual income. Here one way ANOVA compares the variables test scores, compares this continuous response variables, say test score and annual income by a single factor variable, that is level of education. And in this two-way ANOVA example, look at the independent variables, level of education and zodiac sign. Okay, this is zodiac sign. So two-way ANOVA compares two or more continuous response variables, test score and annual income by two or more factor variables. Here two factor variables are taken, that is level of education and zodiac sign. Okay, this is your test score, this is your annual income. Okay, so when comparing two or more continuous response variable by a single factor, a one way ANOVA is appropriate. Okay, comparing test score and annual income together by level of education. A two-way ANOVA also entails two or more continuous response variables but compares them by at least factors. Okay, so compares them by at least two factors. Here comparing a test score and annual income together by both level of education and zodiac sign. Okay, now look at this Mankova, M ANOVA. Okay, so we have learned ANOVA, then look ANOVA, then M ANOVA, then now we have to learn a Mankova. Okay, M ANOVA. So like ANOVA and ANOVA, the main difference between M ANOVA and M ANOVA is the C, which again stands for covariance. Both are M ANOVA and M ANOVA feature two or more response variables, but the key difference between the two is the nature of the independent variables. While M ANOVA can include only factors, an analysis evolves from M ANOVA to M ANOVA when one or more covariates are added to the mix. Okay, look, independent variables factor, one factor is level of education, another is number of hours spent in studying, and they jointly evaluate the continuous response variable, test score and annual income. Okay, so look, M ANOVA compares two or more continuous response variable, that is test score and annual income here. Okay, by levels of factor variable, by levels of a factor variable, that is a level of education, and also by a by controlling for a covariate. Okay, and also controlling for a covariate, that is number of hours spent in study. Okay, understood? Now just open the Jupyter notebook part. Go to this 51st line. There is a file, gender, diet, weight. Okay, this is a CSV file. Just run this snippet of code and tell me whether you have got this following data or not.
Yes, ma'am, getting the same data.
Okay, just wait 1 minute. Have you understood? You can uncomment out. Okay, this line print demailed and print, so can you better understand. Okay, so I've just replaced this so column names, that is the first for the ID where is gender, and for this that block values I have created a column area. Okay, and this is my response variable weight. Okay, Look at this. Okay. Now come to this part. Have to generate a box plot. These genotypes and areas. Okay. It will be areas, not years. Okay. I have given different name now. Genotype you can write or gender you can. That is not years, that is area. Okay. So look at this. You can understand the box plot, the distribution of data. Now look at this. This is your ordinary least square. It will just give the fitted model. Okay. But it will compute the main effect of each factor and the interaction effect. Okay. Now this is your ANOVA. LM type equal to 2. Okay. It's taken here. And then look at the values. Have you all got the same output?
Yes, ma'am.
Okay. So now I want to draw the interaction. Okay. Look at the F statistic and the probability. Okay. If you do the interaction plotting, look, these are almost parallel only with respect to this gender. Okay. The area and block. The area has two levels, now block and diet. So those block and diets have been drawn here with respect to gender. So these are almost parallel. If there is a curve, we can say yes, there is a significant interaction takes place between the groups. Okay. But because this is parallel with respect to gender, we can say no significant difference exists. Okay. Now look, this is your 2K HSD test. Okay. For unequal sample size, you can use 2K Kramer test, whatever. Here we have taken equal sample size. So look, this is your response variable, weight. X factor variable is gender. ANOVA model is this. And this is your 2K summary. Okay. So it will tell you what there is no difference between male and female. Okay. And if you compute this for main effect area, this is for the main effect diet. Okay. Sorry, not diet here. Gender. Have to remove this. So this is the benefit of gender, then this area. You just rectify this, okay? Actually, you can write in that way also. That is the okay. Just wait. You can write in this way. So look at this. The group 1 and group 2, the p-value, and look at this area. There is a two levels, not diet and block. So yes, there is a significant difference between this diet and block. Look at the p-value. And for the interaction effect between this between diet and area with respect to gender. Okay, so and write in this way. For your better understanding, you just change the writing, the comment parts. Okay, I'm telling you. Okay, you can also do one thing. Okay, here I have taken this diet and block. Just wait. Diet and block to be my value variables. Okay, but you can do in other ways. That is, you can take your ID variable as diet and take here gender and block. Okay, so you can do that. Okay. It will be your gender and area. Okay, look at this part. Here we have parsed a list of categorical variables, gender and area. Okay, actually what I did in the previous time, I take my diet to be as ID VAT. Okay, that's why I have not removed the comments. Okay, just look. This is, I have taken here diet and here gender and block. Okay, later I have changed. So the comment part in the commented lines, I have not changed that. So it remains diet. Okay, here, but you have to change the diet with gender. Okay, understood? When you do something else, suppose you change the ID VAT to be diet, then you have to change the in the comment lines, that is it is diet. Okay, whatever you are choosing. Okay, understood? Ujjal, have you understood what I am telling?
Understanding, ma'am.
If you choose ID var equal to diet, then obviously everything gets changed. Okay, then that is if you change ID var equal to diet, then here in the value var is your gender and block, then everything gets changed. Your name, your everything, effect, your box plot, everything gets changed because the xy variable gets changed. Okay, the values of xy and also the values of hue part in the box plot gets changed, everything, because you have changed the combination now. So also in the commented lines, you have to mention that so that people who don't know what you are doing can understand. Okay. If there is a curve, then you can say between these blocks there is a significant difference. Okay. So look at this. I want the interaction effect between gender and area on this response variable weight. Okay. So look, there is no as such interaction effect present. Okay. Look at the p-values. So look at the QQ plot. Okay. So these are not following any distribution. Okay. Look, this is not normally distributed, your residuals. This is not normally distributed. Okay. If you test Shapiro will test to the to check whether they are normal, whether the residuals are normally distributed or not. You can say that. Look at the p-value 2.819 into 10 to the power minus 0.07. So that means it is too small compared to 0.05 or 0.01, whatever alpha you are taking. So whatever alpha you are going to take, so you have to reject the null and you have to say it is not normally distributed. So this is, so here you have to do another test, that is live-in test. Okay, for homogeneity of variance. Okay. So look at this value. The homogeneity of variance is this 0.010, which is less than 0.05. Okay. So you can say that the homogeneity of the residual error, homogeneity of variance is not observed in the residual error. Okay. So it just validates the Twoway ANOVA. The assumptions of Twoway ANOVA. Okay, it just violates the assumptions of Twoway ANOVA. So either I have to prepare my data so as to make it normally distributed with respect to the categorical variables, and also I have to do, I can conduct non-parametric test Kruskal-Wallis where median of the groups need to be checked. Okay, for equality. Okay, and when you want to learn about the difference in groups after conducting the Kruskal-Wallis test, okay, which is a non-parametric test. So in order to learn about the difference in groups, that is which groups are different, okay, you have to conduct this 2K HSD test. Okay, understood? For interaction, you have to pass all those variables. Okay, here only two categorical variables are present, so gender and area are passed. Okay. Actually, there are three categorical variables. One is your diet, first is your gender, another is diet block. But diet block needs to be passed to these value variables so that you can give them a particular column under which these values of diet block belong to. Okay, that is area here. You can give any other name. I have given here area. Okay. So here you can say that this area, in this area, look, there is a significant difference between diet and block. Okay. If you consider if you consider the alpha 0.05, so look, p value is too small compared to this. Okay. So diet and block individually has a difference. Okay. That is, the mean of diet and block is not equal. Okay, that is, the mean difference is not equal to 0. So they have a significant impact on the response variable weight. Okay, that is, if your diet is diet and block do not have equal impact on weight, there is a there is a significant difference in mean, that diet may be more or block may have more impact on the response variable weight. Okay, block means block size, diet means the amount of diet. Okay, you can say. Understood? Look at this area part. So area has an impact because there is a difference between block and diet. Now, there is a difference in the group mean between block and diet. Okay, so look at this. But with respect to gender, that is your interaction plot here. Look, gender, there is no interaction effect is observed. Okay, this plot is true. And how can you check that? When you check this interaction effect between gender and area, you get all the p values greater than 0.05. Look. Okay. And with respect to gender, that is gender into this part. If this is this part, okay, the C gender colon area, that is the interaction effect. So when you draw the interaction effect, that is gender with area on this mean of weight, then if you have found out parallel lines, that means there is no such interaction effect on this. There is no as such a significant interaction effect on this mean of weight. So if there is a curve, then you can find out different results. Okay, then that interaction effect becomes significant. Okay, so this is the way of interpreting and understanding two-way or n-way ANOVA. Okay. So have you understood up to this part, Ujjal, Shima?
Yes,
Yes.
ma'am.
Okay, so you have understood up to this part. And if you have any problem, you can let me know. Okay, Anish, are you there? Anish, are you there? Anish, you can stop recording.